In this video, we will learn how to describe and illustrate coordinate covalent bonds in simple molecules and metal compounds. Molecules are formed when two or more atoms bond together. The atoms may be the same element or from different elements. It does not matter. When the atoms that are bonded together are non-metals, they are held together by strong covalent bonds. Ammonia is an example of a molecule that contains strong covalent bonds. One nitrogen atom lies at the centre of the molecule and it is bonded to three hydrogen atoms. Notice that both of these elements are non-metals. In ammonia, three single covalent bonds are formed. Each bond is a normal single covalent bond. A covalent bond, remember, is a shared pair of electrons. In a normal single covalent bond, one electron comes from each atom in the bond. The central nitrogen atom has 5 valence electrons. Remember that nitrogen is found in group 15 or 5 of the periodic table. Nitrogen uses up 3 of its valence electrons in forming these bonds. Because a nitrogen atom has 5 valence electrons, there are 2 valence electrons left over. These electrons form a lone pair. A lone pair is a pair of electrons found in the outer shell of an atom that are not involved in forming any covalent bonds. The structure we see here for ammonia is known as a dot-cross structure or a dot-cross diagram. In this structure, dots represent valence shell electrons for the nitrogen atom and crosses represent valence electrons for the hydrogen atoms. Dots and crosses are placed in overlapping circles to represent single covalent bonds. Lewis structures may also be used to indicate bonding pairs of electrons and lone pairs of electrons in the molecule. A Lewis structure is a little different to a dot-cross diagram as each pair of electrons is represented by 2 dots. Whether we use 2 dots or straight lines to represent the bonding pairs of electrons in our Lewis structure for ammonia, the lone pair of electrons is always visible. An ammonia molecule can form an ammonium ion by using the lone pair of electrons that are located on the central nitrogen atom to form a coordinate covalent bond. When a coordinate covalent bond is formed, this lone pair of electrons on one atom is used to form a covalent bond with another atom that does not have any electrons available to share. The atom donating the electron pair into the coordinate covalent bond is called the donor atom. The atom receiving the electron pair must have a vacant orbital. In this case, the proton or H+ ion can accept the lone pair of electrons into its vacant orbital. The H+ ion does not have any electrons available to share. In the ammonium ion, which contains a coordinate covalent bond, nitrogen is the donor atom and hydrogen is the acceptor atom. A coordinate covalent bond can also be known as a dative covalent bond or simply as a coordinate bond or a dative bond. It's important to realise that a coordinate covalent bond is just like any other single covalent bond once it's been formed. It's just the origin of the shared pair of electrons that is different. When using a displayed formula, a coordinate covalent bond is shown using an arrow. The direction of donation is indicated by the direction of the arrow. Notice that in the ammonium ion, the arrow is pointing from the nitrogen donor atom to the hydrogen atom, which is the acceptor atom. This arrow is not seen in a dot-cross diagram or a Lewis structure. Another feature of the displayed formula of the ammonium ion is that the positive charge that exists on the nitrogen atom is also shown. It may be seen located on the nitrogen atom itself or placed outside square brackets that surround the entire structure. Many other examples of coordinate covalent bonding exist. Hydrogen ions do not exist in isolation in liquid water. If a hydrogen chloride molecule is dissolved into water, a hydrogen ion is transferred from the hydrogen chloride molecule to the water molecule. The water molecule contains two lone pairs of electrons. Water can use one of these lone pairs to form a coordinate covalent bond to the hydrogen ion. This reaction forms the hydronium ion H3O+ and a chloride ion. The hydronium ion H3O+ may also be referred to as the hydroxonium ion in some texts. The hydronium ion contains a coordinate covalent bond. Notice that the molecule has a net positive charge as a result of the oxygen donor atom, which originated in the water molecule, donating one of its lone pairs to the hydrogen ion, which originated in the hydrogen chloride molecule. Carbon monoxide is an oxide of carbon that is formed when hydrocarbon fuels are burned in a limited supply of oxygen. It is a poisonous gas and its formation must be avoided in domestic homes when fuels are ignited. Carbon monoxide consists of one carbon atom and one oxygen atom. The carbon atom uses two of its valence electrons to form two covalent bonds with the oxygen atom. The oxygen atom uses a lone pair of electrons to form a third bond to carbon, which is a coordinate covalent bond. There is no net charge on the molecule of carbon monoxide. In the displayed formula of carbon monoxide, the coordinate covalent bond is again shown as an arrow, indicating the direction of donation. If ammonia reacts with boron trifluoride, the lone pair on the nitrogen atom in ammonia can be used to make a coordinate covalent bond with the boron atom in boron trifluoride. In BF3, boron is electron deficient, having only 6 electrons in its valence shell. If boron becomes the acceptor atom, a nitrogen to boron covalent bond is made, and boron fills its valence shell. Nitrogen is the donor atom in the formation of this coordinate covalent bond. Using a displayed formula for this molecule, an arrow from the nitrogen atom to the boron atom is used to show the coordinate covalent bond. Lewis acids are defined as species that can accept a pair of non-bonding electrons or a lone pair of electrons. In all of the examples of coordinate covalent bonding that we have seen so far, the acceptor atoms in the bond could be described as Lewis acids. In the molecule NH3BF3, the boron atom is the acceptor atom. It's behaving as a Lewis acid. A Lewis base is a species that can donate a lone pair of electrons. In all of the examples of coordinate covalent bonding seen so far, the donor atoms are behaving as Lewis bases. Metal ions that are placed into liquid water attract water molecules very strongly. This is because metal ions are relatively small and may have a high positive charge, such as the aluminum 3+ ion. The attractions are so great that coordinate covalent bonds are formed. The water molecules contain lone pairs on the oxygen atoms, and these are the donor atoms in this case. One aluminum 3+ ion can form 6 coordinate covalent bonds to 6 separate water molecules. Only one lone pair is used by each water molecule to form these coordinate covalent bonds. The other lone pair is pointing away from the aluminum atom, so it isn't involved in the bonding. The aluminum atom accepts these electrons into some vacant orbitals. The 3+ charge on the aluminum ion is now evenly distributed across the entire molecule. Since only 6 water molecules will fit around the central aluminum atom, this ion is known as the hexa-aqua aluminum ion. Now it's time for a question to test your understanding of coordinate covalent bonding. An ammonium ion NH4+ contains one coordinate covalent bond. Which of the following displayed formulas correctly shows the structure of an ammonium ion? In the ammonium ion, which has the formula NH4+, nitrogen is the donor atom as far as the formation of the coordinate covalent bond is concerned. We're being asked to identify the displayed formula of the ammonium ion in this question. The displayed formula shows all bonds and all atoms in the structure. All of our possible structures here show the correct number and type of atom for the ammonium ion. Each possible structure contains one nitrogen atom and 4 hydrogen atoms present. All of our possible structures have the positive charge located in the right place. When writing displayed formulas, we use a straight line or a dash to represent normal covalent bonds, and we should use an arrow to represent coordinate covalent bonds. In this case, the arrow must show the correct direction of donation of the lone pair. That is, from the nitrogen atom to the hydrogen atom. Remember that the nitrogen atom is the donor atom and the hydrogen atom is the acceptor atom in this bond. The only structure here that is using the correct notation for a displayed formula is structure E. It's the correct answer. Let's see why the other answers are not correct. In structure A, we see a dotted line used to represent one of the bonds. A dotted line is often used to indicate that a bond is not a full bond, it's only a partial bond. An example of this would be a hydrogen bond formed between 2 molecules. Although ammonia molecules can form intermolecular hydrogen bonds, this dotted line does not represent the coordinate covalent bond in the ammonium ion. This structure is therefore an incorrect answer. In structure B, we see one of the covalent bonds represented as a wedge shape. A bold wedged line indicates that the bond is protruding out from the plane of the drawing surface. It's pointing out of the page. This structure does not represent the correct three-dimensional shape of this molecule, and it does not show the coordinate covalent bond either. It's not the correct answer. Structure C includes a wavy line as one of the covalent bonds. A wavy line is used when the true stereochemistry or direction of the bond is unknown. This is not a displayed formula and it doesn't contain our coordinate covalent bond, so it's not the correct answer. Although structure D is very close to the correct answer, there is no coordinate covalent bond depicted by an arrow shown at all. It shows 4 ordinary covalent bonds and it's therefore not the correct answer. The correct answer is therefore structure E. Now let us review the key points about coordinate covalent bonding. A normal single covalent bond contains one shared pair of electrons between atoms. In a coordinate covalent bond, the shared pair of electrons originates from just one of the atoms. The donor atom in a coordinate covalent bond must contain a lone pair in the valence shell. Examples of molecules that contain coordinate covalent bonding include the ammonium ion, the hydronium ion, and carbon monoxide.